So I wanted to do a short video that gives you an introduction into the idea of electric fields. So in chapter 5 of your book, we learned about the Coulomb force that describes the force between two charges. That would be written as, right here I'll put it down, F equals K, Q1, Q2, over R squared. So that's the expression when I'm talking about the force, the Coulomb force between two charges. And so we just basically say, hey, we know that opposite charges attract and like charges repel, but then we're told this expression allows us to calculate how big that force is. Boom, just given to us. But we also want to give you another way to think about, like, why would two charges have some sort of force interaction? And the way that we are going to do that is through this concept of an electric field. Basically, what we say is that an electric field will be created by a charge. So every charge creates its own electric field, and it permeates space around that charge. So it doesn't just sit on the charge itself, but anywhere around the charge, there is an electric field. We can't see it, it's invisible, but it does exist, and it has a certain strength and direction. Then what happens is we think about the fact that when another charge comes near the first charge, so we have this first charge, created an electric field around it, and now another charge comes nearby, it enters that electric field and it feels a force. So we're going to explain that force between two charges in a different way, say it's as a consequence of the electric field of the first charge. So this idea of a field is something that we have in physics. We talk about really what it is it's shorthand for the term force field. But we never say force field, we just say field. But having in your mind that it's a force field might be helpful to you to think about, like, what exactly do we mean? Basically, it's something that's in space. I always think it's kind of like science fiction, where you knew that there was a force field around, say, the spaceship, but you didn't really see it unless another ship tried to enter into that space and it kind of like got stopped, or other similar science fiction-y type examples. So we can't see it, but we can see its effect. And that's exactly what we have in physics when we talk about these fields. Basically, so the field is permeating space around an object. It's caused by something about the object, some quality about it. And when another object enters into that field, it feels a force. And that's why we call it a force field. We actually have already talked about a field last semester, and we talked about something that we were more familiar with. We called it the gravitational field. And we said that the reason that, say if we're talking about the Earth, and the way that an object falls to the surface of the Earth, we could think of it as that force of gravity that exists between the two objects. But we could also say it's because the object entered into the gravitational field of the Earth, therefore it felt a force and it was pulled down. And what I want you to also think about is, when we're talking about this idea of the force of gravity and the gravitational field, I also want to remind you of how we calculated the force between two masses due to their gravitational attraction, and I want you to see that how similar these two expressions are. And if you had me last semester, you know that I warned you that this would come up. And so in both of these cases, both with the electric field and the gravitational field, we had an expression already for how we calculate the force, but then we thought of it in a different way. So here is a picture showing the gravitational field of a mass, and the gravitational field is pointing in towards it. The way that we define it is if we have a little mass that comes near it, the force that it feels, well, is equal to m times that gravitational field. Look familiar? Or maybe another way to think about it is we might have been told that the gravitational field that was surrounding this mass could be found if we calculated the force that was exerted on a small mass that entered into its gravitational field, but then we divided by the mass. And so if we look at this, this would have been big G, big M is this guy, over r squared, but then we divided by little m, and this gave us G, big M over r squared, and we called that the gravitational field. Therefore, we could also say that the force that this small mass felt, we could actually find by taking this expression and multiplying it by little m. You see that we get back to this one. So hopefully that's not too circular, but I felt like we're usually pretty comfortable with the idea of the gravitational field. And if we can kind of absorb that, then it makes it easier for us to think about the electric field. So the electric field is super similar. Again, we're going to think about how a charge is going to create the field around it, and when a charge enters into it, it feels a force, and we can then define the electric field in that way. So in this picture, we show the electric fields due to two different types of charges. We have our positive charge and our negative charge. And the positive charge creates electric field going out away from it, where the negative charge creates an electric field going in towards it. And the reason that this happens is because we imagine our little small charge. Our little small charge is always positive. And I'm just going to call this bigger charge right here. We're going to call that big Q, just to make it obvious. And what we would say is when this charge enters into the electric field, what kind of force will it feel? Well, we know it's going to feel repelled. It's going to feel repelled. It's going to feel pushed away. And that force divided by that charge can be used to express the electric field. And because the force was away, that's the direction of the electric field. Similarly, if I put this little positive charge here, it actually feels attracted. And that electric field is that force divided by that charge. And so because of the fact that the force was towards the charge itself, that negative charge, that's the direction of the electric field. So again, we kind of define the electric field as the ratio of the force that a positive charge would feel if it entered into the electric field, but then we divide by that charge itself. If we compare this expression to this expression, we should see that the electric field can be found by the expression of KQ, big Q, which is the charge that's causing it. So that would be either these big positive or negative charges divided by the distance away from the charge itself. And that's how we find that electric field. So again, the other thing that I want to point out is when you look at these field lines, these arrows representing the electric field, they tell us two different things. The arrows point in the direction of the field, so that tells us the direction. But you can also see that when we're close to the charge, the field lines are closer together, and as we get further apart, they get spaced out further apart from each other. And so that's another thing that those electric field lines are telling us. The density of the lines tells us the strength of the electric field. So these electric field lines, the reason that we draw them is we're trying to visualize this electric field, which, remember, it's invisible, and so it gives us a way to visualize. Finally, the last thing that I want to mention in this is that if you have several charges, they all create their own electric fields, And when we want to find the total electric field, we have to add all the individual contributors, but add them as vectors. Now this is a picture from your book, and in this picture what we're trying to do is we have several charges in this space. The blue charges are actually positive. I don't think you can see the signs on the screen, but the blue charges are the positive ones and the reddish, yellowish, brownish ones are negative. And all the arrows here are numbered, just like the charges are, to represent the direction of the electric fields caused at point P, which is where we're being asked to find the electric field due to all these charges added together. And so just some things to keep in mind, like mentioned here, like charge 7 is a positive charge, and notice E7 is pointing away from it. And so that's consistent with what we've learned. One that is negative, we have Q2 is positive. This is Q5, I believe. And we also see E5 over here. So E5 is pointing towards the negative charge. And so sorry that it took me a while to see that. Another one would be, this is Q6, and over here is E6, again pointing towards the negative charge. In the next video, I show you how to actually do the mathematics of adding those together. So hopefully this helps a little bit in the idea of what an electric field